This is Joel Denny from Oak Ridge National Lab, and I'll be talking about our ongoing work to develop OpenACC C support for LLVM. I'd like to acknowledge the Exascale Computing Project, ORNL's experimental computing laboratory, and the Oak Ridge Leadership Computing Facility for their support. First of all, what is Clacc? Clacc is a project to develop OpenACC C support for C and C++ as an extension of Clang and LLVM. The key design decision we made at the beginning of the Clacc project is to translate OpenACC C to OpenMP in order to build on the OpenMP support being developed by a number of different organizations. On this slide, I've provided the URL for Clacc's ORNL homepage, and I provided the URL for Clacc source code, which is hosted publicly on GitHub as part of the LLVM DOE fork that we maintain at ORNL. Clacc is funded by the Exascale Computing Project, or ECP, and I am the primary developer and contact for Clacc. I mentioned that the Clacc compiler translates OpenACC to OpenMP, so I want to clarify what that means for Clacc users. There are two compilation modes. The first and most important mode is traditional compilation mode. By that, I mean translation from OpenACC source to a binary or executable, similar to what MVHPC or GCC does. For this mode of Clacc, OpenMP serves purely as an intermediate representation, very similar to the role of LLVM or assembly language, and the user does not need to be exposed to OpenMP. For this mode, translating to OpenMP enables Clacc to maximize its reuse of the OpenMP implementation. Because Clacc translates OpenACC to OpenMP for the sake of traditional compilation, it seems reasonable to expose the OpenMP source to users who want it. So this is the goal of source-to-source mode. Why would a user want to generate OpenMP source? There are many possible reasons. For example, a user might want to target a different OpenMP compiler that offers some optimization or architecture support that upstream Clang doesn't yet offer, so that he can bring that support to OpenACC. Another possibility is to port apps from OpenACC to OpenMP. To better support both use cases, Clacc's source-to-source mode uses Clang's rewrite facility to avoid the preprocessor expansions and loss of comments and formatting that are common in source-to-source efforts for C and C++-based languages. This is important to keep the generated OpenMP human readable, and because when using other OpenMP compilers, perhaps targeting other architectures, such preprocessor macros might expand differently than under Clang. So one important question is whether OpenMP can actually represent all the features required for translating OpenACC. The answer is no, it cannot. So I'd like to divide these cases into two categories. First, there are unrepresentable individual behaviors. For example, OpenACC specifies 2 reference counters for tracking allocations on target devices, a structured reference counter and a dynamic reference counter. But OpenMP specifies only 1. Some OpenACC applications will not function correctly if you attempt to implement them with only 1 reference counter. You will end up with premature deallocations from device memory. Second, there are unrepresentable ranges of behaviors, each of which is individually representable. For example, using OpenACC's auto clause, the OpenACC application developer can specify that they're not sure whether a loop's iterations are data independent. So the compiler must make this determination. If it can parallelize the loop. If it cannot, then it must execute the loop sequentially. In OpenMP, we can certainly represent the sequential loop or the parallel loop, but we cannot represent the auto clause's possibility of either case and the condition for choosing between them. So how does Clacc handle OpenACC that is unrepresentable in OpenMP? Clacc's solution is to devise OpenMP extensions. Of the various solutions we have considered, we found that the use of OpenMP extensions has many advantages in the compiler design. They can handle both unrepresentable individual behaviors and unrepresentable ranges of behaviors. They can do so in both traditional compilation mode and source-to-source mode. They enable the compiler to fully transition from the OpenACC representation to the OpenMP representation in one compiler phase, never finding itself in some sort of mixed, partially translated form. And as is the norm in the LLVM ecosystem, complex analyses and transformation passes can be implemented at the level of LLVM rather than at the Clang AST level. Another advantage is that this approach follows OpenACC history by encouraging contributions to the OpenMP specification. But what is the impact of OpenMP extensions on Clacc users? For traditional compilation mode, there is no impact. OpenMP is just an internal IR, and the Clacc compiler quietly uses OpenMP extensions as needed. The user doesn't need to know. For source-to-source mode, there's a caveat. In this case, the user may wish to compile the generated OpenMP source with a different OpenMP compiler that doesn't support Clacc's required OpenMP extensions. For this reason, to be sure the user is aware, Clacc source-to-source mode by default produces a compile time error diagnostic if the OpenMP translation uses an OpenMP extension. The user then has several options. The user can disable the diagnostic for that extension in case they know the OpenMP compiler they'll target does indeed support the extension. For example, we have begun upstreaming these extensions to Clang and LLVM, so they should eventually find their way into vendor forks as well. Alternatively, the user can convert the error to a warning to make it easier to find all cases where the extension is required, and then adjust either the original OpenACC source or the generated OpenMP source not to need it. Finally, Clacc provides command line options that use alternative translations to standard OpenMP features that might not represent the exact semantics of the original OpenACC, but that might be good enough for some application. So far, I've talked about Clacc's OpenACC directive support. What about Clacc's OpenACC runtime library and profiling interface support? Here too, Clacc's strategy is to build on OpenMP plus extensions, and there are similar advantages. To this end, we implement Clacc's OpenACC runtime in a library called libacc.omp, which serves as a wrapper around the OpenMP runtime. Currently, it's only tested with LLVM's OpenMP runtime. However, we have carefully defined libacc.omp's interfaces to facilitate extending support to other OpenMP runtimes in the future. These interfaces should also facilitate maintenance within LLVM itself. To support the OpenACC runtime library routines, libacc.omp wraps standard OpenMP routines, plus some original OpenMP routine extensions. To support the OpenACC profiling interface, libacc.omp wraps OpenMP's OMPT plus original OMPT extensions. And to support OpenACC environment variables, libacc.omp requires the OpenMP runtime to call handler routines provided by libacc.omp. So what's the status of the Clacc project? For directives, Clacc supports various critical features with a few notable exceptions. Most recently, we added support for the ACC routine seek directive, and we're working on other clauses. This past year, we added support for most runtime library routines, the underscore OpenACC preprocessor macro, and all environment variables. Clacc's OpenACC profiling interface support includes most profiling events and profiling data. This past year, we've added support for bar name. And working with our University of Oregon collaborators, we also integrate with TAL and published that work at the Pro Tools workshop at SC20. Clacc is regularly tested on x86-64, Power 9, and NVIDIA GPUs. We are working on testing support for AMD CPUs and GPUs as upstream LLVM's OpenMP support on AMD improves. This past year, we set up issue tracking for Clacc within the LLVM DOE fork in GitHub. So far, we're using this to identify potential projects for external collaborators, rather than using it to track all of our own efforts, but that usage may evolve. We try to stay in sync with upstream Clang and LLVM. That means merging upstream changes into Clacc. It also means contributing various changes back. For example, OpenMP, Clang, and testing infrastructure improvements. One especially noteworthy upstream contribution recently is our dual reference counter support and an OpenMP directive extension to use it, the hold map type modifier. And finally, we continue to contribute to the OpenACC specification, and we're beginning to get involved with the OpenMP spec. I should point out that Clacc includes a status document that details exactly what's currently implemented, and you can find that on GitHub in Clacc's main branch. There's one last topic I want to bring up. What about Fortran OpenACC support? Flacc is a project to develop Fortran OpenACC support in upstream LLVM Flang, not to be confused with classic Flang. This project has also been funded by ECP, and the primary developer has been Valentine Clement. An interesting difference from Clacc is that Flacc does not translate OpenACC to OpenMP. Instead, it lowers OpenACC to a mix of the FIR dialect and the OpenACC dialect in MLIR. I'll talk more about that in a moment. Moreover, Flacc is upstreamed as it's developed, whereas Clacc's OpenACC support has only just begun to be upstreamed. I've not worked directly on the Flacc project. Please feel free to reach out to Valentine for detailed questions. Valentine sent me this diagram to depict the design of LLVM Flang. This design includes both OpenACC and OpenMP support, but we want to focus on OpenACC, so I'm going to gray out the OpenMP parts to avoid confusion. As you can see, LLVM Flang, which used to be called F18 as it's labeled here, parses Fortran source into an AST, which is then lowered to MLIR. In case you're not familiar with MLIR, it's a multi-level intermediate representation, originally from Google, that is becoming popular in the LLVM community for defining IR dialects, which are similar to LLVM's original IR, but they can represent higher level constructs and they can be lowered to LLVM IR. Flang lowers OpenACC Fortran code to a mix of an OpenACC dialect developed by Valentine and FIR, which is a dialect developed by NVIDIA to represent Fortran. The result can be lowered to LLVM via various other dialects developed by the LLVM community, including GPU dialects. And optimizations can be performed at many different levels. Finally, I want to briefly discuss the planned implementation reuse between the Clacc and Flacc projects. First, let's look at the OpenACC directed support and the compiler frontend. Clacc's compiler frontend is based on Clang, which does not support MLIR, and as far as we know, might not ever support MLIR. Flacc's compiler frontend is based on Flang, which is designed to target MLIR. That is, the designs of these frontends are very different, so we made different design decisions for the corresponding OpenACC support, and we currently don't foresee many opportunities for reuse. However, at the runtime level, we expect directed support to easily be reused. Both Clacc and Flacc use LLVM's OpenMP runtime. Both should benefit from Clacc's OpenMP runtime extensions, such as the dual reference counter support that I mentioned earlier. For OpenACC runtime library routines, libACC to OMP C routines directly support Clacc. We expect that libACC to OMP will grow Fortran routines that wrap the C routines, but we haven't started implementing that yet, so plans may evolve. For the OpenACC profiling interface, reuse seems straightforward. Because this interface is for profiling libraries, such as TAL, the OpenACC application language, C or C++ versus Fortran, is irrelevant. Thus, we expect Flacc to reuse libACC to OMP's profiling interface support from Clacc without modification. Likewise, for OpenACC environment variables, we expect Flacc to reuse libACC to OMP support for Clacc without modification. Okay, I'll leave you with a summary slide. Key URLs, contact info, and publications are on the right. Please reach out if you're interested in working on OpenACC and LLVM. Thanks.